Hello, I'm Clint Dawson, the chair of the Department of Aerospace Engineering and Engineering Mechanics here at UT Austin. Thank you all for coming to our inaugural ASE EM Distinguished Lecture Series. To kick off this new series, we're pleased to welcome John Junkins, a distinguished professor of aerospace engineering and the founding director of the Hagler Institute for Advanced Study at Texas A&M University, also a member of the National Academy of Engineers. Dr. Junkins' half-century plus of academic appointments have been at the University of Virginia, Virginia Tech, and Texas A&M. He collaborates frequently with governmental and industrial partners and is a prolific mentor. In fact, half of his 58 PhD students have gone on to become professors, giving rise to a three-generation family of around 160 PhD descendants. John's time shares various university leadership roles with research and graduate student mentorship. His interests span astrodynamics, estimation, controls, space robotics, and optical sensing technologies. He does analysis, computation, design, inventions, and experiments. He's published 7 books, 7 patents, and 350 archival papers. His results have been realized successfully in several space missions. Today, Professor Junkins is here to share progress on his work with his PhD students, Patrick Kelly and Sandeep Singh, which was motivated by a renewed interest in cis-lunar space, vehicle operations, and other lunar missions. John, we welcome you to University of Texas and to the stage.
Thank you so much, David. It's my pleasure, great pleasure to be here today. I was trying to remember today my last previous visit here, and we had a little trouble, but we finally reconstructed. It was 19 years ago, I think, roughly, when I last visited for a seminar. But I do remember vividly the first time I came here. I was telling Byron Tapley this morning that he invited me to come to give a seminar when I was on the faculty at the University of Virginia, sometime in the 75, 76, I don't remember the exact year in that time frame. And while I was at the University of Virginia, we had probably the worst football team in the history of Division I football. We lost 27 consecutive games, followed by 1 win, followed by 23 consecutive losses. And in the middle of that a world-class incompetence on football field, the coach at the University of Virginia and athletic director had the audacity to schedule Texas at Texas while this really incompetent player named Earl Campbell was here. And so in the midst of his run toward the Heisman Trophy, UVA came out and got beat 69-3, but it wasn't quite that close. But at halftime, it was, about, 35-0. And so anyway, Byron, I don't know how many of you know Dr. Tapley, but he has what I call a sandpaper voice. And when he was introducing me, he said, John, the University of Virginia was just out here 3 weeks ago. And let me tell you, we were impressed. He said, I'm not talking about your football team. But at halftime, in front of 80,000 screaming Longhorns, your cheerleaders brought around a placard to show to the fans, and it said, we were the, in italics, University of Virginia before Texas was a state. And Byron said, I thought that showed a certain moxie, and we admire that. So that was my recollection of my first trip here. I'm here today to take credit for Patrick Kelly's work with a little bit of input from me. And we're looking at a problem. I won't read this to you, but basically, we'll see in just a moment, there's some invisible mathematical surfaces that exist that have tremendous import and theoretical import in the restricted three-body problem. There are some orbits in the vicinity of mainly the straight line version of the Lagrange libration points that come up out of the plane in the vicinity of these points. And these orbits are fairly fragile. They're quasi-stable. There are certain directions in space that are stable approach occurs, and certain other directions where rapid departure results. But these ones where you have a stable approach, that part of state space, if you numerically integrate backwards from every point around the orbit, you generate a surface, which if you turn time around and coast, you will asymptotically fly for free with no propulsion back onto that surface. And these mathematical surfaces are kind of like tubes in the sky, and some of them extend back rather usefully toward Mother Earth. And so the question that we were looking at, first of all, and we'll proceed to the schedule or through these slides a little more efficiently in a minute, but the first question that I asked Patrick was, okay, we know optimal control theory. Suppose I wanted to start from GEO in an existing orbit and use low thrust propulsion to spiral out. How do I incorporate that infinity of possibilities on this coast manifold so that I find the right patch point that is optimal in the sense that it minimizes fuel? Because these slow coasts are suitable for resupply missions and scientific missions, not for astronauts. These tend to be fairly slow, but we want to use inexpensive low thrust propulsion to do that. That's question one. How do we do that for the circular, restricted, idealized three-body problem? We'll go over the math in just a moment. But then we know these orbits that we're trying to get to are fairly fragile. They're artifacts of quite a few idealization assumptions. Assumes the Earth and the Moon are perfect spherically symmetric bodies in perfect circular relative motion, ignoring the sun and ignoring all other gravity anomalies. So the question is, how can we make these beautiful artifacts of the three-body problem and optimal control theory, how can we make that useful with a high fidelity model that's required for a mission? So that's the question that we were pursuing here. And I know not all of you are three-body fans, and some of you can do it in your sleep. I'm going to bore those of you who know the three-body problem by a very quick short course. I think. We aren't advancing. Okay, this is an outline. We're going to look at the three-body problem. And then we're going to look at a way these mathematical surfaces, we've got to be able to represent them mathematically, ultimately with very high precision in a high fidelity model. So we're going to do some approximation theory, and then we'll look at the optimal control formulation last. I'll get it going in a minute here. So here we have the, first of all, it's just in general for the N particles, if you simply sum up and I see I'm missing a third power here that should be the product of the masses over R squared if I make that a unit vector, and over R cubed if I got it regular. So I'm missing a coefficient there. You know, every time you look at a set of PowerPoints in real time, you see arrows that you missed and you're when you're writing them. But basically, I know how to write the differential equations. If I get initial conditions, I can integrate the particle motion and the n-body problem. But if you restrict it down to the three-body problem, it turns out the problem is not completely analytically integrable. It's not completely solvable, even when you restrict it in a circular restricted three-body problem. But the two-body problem, which is only the Earth and a particle, forget the moon for a moment if we think of this Earth-moon particle, the Earth and one particle, or the sun and one planet, that problem was solved originally before we knew the physical laws and before we even knew calculus. By Kepler, he solved it by taking given measurements and uncovering the underlying analytical solution, and it turned out it was almost 100% correct, even though he didn't do it in a forward problem. But Newton's solution of the two-body problem was the most important development, of the Renaissance, as far as I'm concerned, an egocentric reference frame, because he validated his calculus, differential equations, universal gravitational law, and invented all kinds of little tools along the way and made believers out of everybody about Principia. So all of the tools that we use in Newtonian mechanics were first made believers of the respectable in the scientific community because he solved from first principles the analytical two-body problem. So the circular restricted three-body problem, that's where you assume the Earth and the Moon are spherically symmetric bodies in circular motion about their common mass center. The B is the barycenter. And we non-dimensionalize this problem using the distance between the M1 and M2, and M3 is sufficiently small that it's an infinitesimal in principle, but sufficiently small that it can't perturb the larger bodies. And in reality, it's about 16 orders of magnitude between anything we can fly and the smallest these masses. So it's a good assumption for spacecraft. And if you do that and write the inertial acceleration, but project it onto the rotating axes that are, in the case of the Earth Moon, going around each other about every once a month, then these equations can be brought to this form. This term is Coriolis acceleration. There would normally be a frequency term here, but that's been absorbed into time. This U star over here becomes just not really a potential because it has got this term added to it. It's a faux potential. It looks like a spring, but that turns out to be the centripetal acceleration. It ends up showing up as x squared and y squared, and the potential form. The gradient of this gives a centripetal acceleration. So this set of equations has one exact integral, and it's basically the energy integral in disguise. When you write it in a rotating coordinate system, Jacobi did it first. It's called a Jacobi integral, but it's really an energy integral. It gives velocity as a function of position, as is evident, and these are position coordinates. And this C is really the energy constant. And it's amazing how much information you can get out of this energy surface and insights about how to go about extracting information about the motion. The first observation is that if you choose a C that corresponds to a specific points of initial position and velocity, and set the velocity to 0, and you think about that a minute, because the infinity of positions are hidden in the C equation, then what you just did was bound all possible apogee states in this rotating coordinate system. So velocity goes to 0. So they're called the zero velocity surfaces. And you sweep energy, you'll find that the motion is constrained to lie in certain parts of the Earth-Moon space. And by the way, if the energy is such that you're very near the Earth, then guess what? That surface will be a circle. In the two-body world, that would be a circle of twice the same major axis of the orbit. So a rectilinear orbit, all infinity of rectilinear orbits generate all the apogee states near the Earth. And similarly, there'd be another spherical region around the Moon. So there's two spherical regions there for the near Moon, near Earth, and all kinds of other things, and it allows open trajectories in between. And if you look at the front cover of Schaub and Junkins, you will see a beautiful picture. But I'm going to not do all those pictures today. Let's go look briefly. Euler first discovered or asked the following question. He said, I wonder, along the straight line between the Earth and the Moon, if there is a point of no return, to the right of which, thinking of it heuristically, the Moon dominates, and to the left of it, the Earth dominates. But in the dynamical sense, because this is a rotating coordinate system, that point is actually making a circle around the barycenter. But it's in a straight line configuration with the Earth Moon, which are rotating at that same rate. So essentially, you can think of it as that when you include r omega squared for centrifugal acceleration, that gives, I don't like the term centrifugal force, but mass times centrifugal acceleration look like a force, but that sort of circular orbit speed with where gravity is partially canceled, Earth's gravity is partially canceled by the moon. That's sort of a local circular orbit speed, where the circular orbit speed is exactly the period of the Earth-Moon system, so you stay in that fixed position. Likewise, a similar heuristic logic, but you can do the math. L2 has got the combined conjunction gravity, and there's another judicious velocity that would correspond to a circular orbit speed with a 1 month period. And likewise, there's one over here hiding behind the Earth, or whatever the third body is. Less intuitive, and I won't beat on it, but there are 2 points, L4 and L5, which have the property that if you write the gravity force from M2 and the gravity force from M1 and do a vector sum, guess what? It goes right through the mass center of the barycenter, which is a fixed point. And that gravity, if you ask in the sense of a circular orbit speed, would give you the velocity that would match the angular velocity of this barycenter to L5 and barycenter to L4 line, which rotates once per month. So this fixed geometry is there. And Lagrange in 1776 won the Paris Prize for studying the stability of these points. And all 3 straight line solutions were unstable, and L4 and L5 to linear approximation as purely imaginary eigenvalues. So they look like they're circulatory motion in the vicinity of those, but in a nonlinear sense, they're only quasi-stable. So understanding all that has been around for a long time. It took us a while to exploit it, but it's been around a while. Well, in the vicinity of L1, the first time I saw an orbit like this this is a whole family of orbits corresponding to sweeping the Jacobi constant. These are called the northern L1 family, and this is the southern L2 family. There's a northern one out here as well, but I saw the northern one of this L2 in a paper by John Breakwell, and I read it sometime in the late 60s, early 70s. I don't remember exactly when, but I was amazed that this orbit looks like a halo around the moon. If you look at it from the Earth, it comes up out of the orbit plane. And Breakwell produced a number of students, most prominent today among them is Kathleen Howell, who basically built her career largely around studying the properties of these orbits and how to utilize them in missions. So each one of these, if you pick one of these out and analyze it, we can choose one of these, and we will choose one of these subsequent in motion, but they're unstable. But if you study the stability, if you go to any point in the orbit, and which is a perfectly periodic orbit, if you find the initial conditions that will close at some time later, and you say, what's the stability of that orbit? Well, in the original paper that I read by Breakwell, he said, hey, that's a periodic system. And if you look at the state transition matrix from time 0 to 1 period later, the eigenvalues of that state transition matrix evaluated over a period, the eigenvalues of that matrix control the stability. And there are 6 eigenvalues. And that's really where this analysis starts. I keep wanting to walk back to my computer to control it. That's the reason I've got getting lost here. I'm sure it has nothing to do with aging. Okay, nothing whatsoever. No, not possible. Well, one of the tricks to finding periodic orbits is to introduce a cutting plane. And if you've got some idea that there ought to be a periodic orbit in that part of sky, then you can start at x0 and you can iterate. Let's suppose you fix the position coordinates and vary the velocity. You can say, can I get this orbit to close when it comes back through that cutting plane. And if I iterate on those conditions, and there's a lot of literature on that, how to create a periodic orbit. So it's introduce a cutting plane and essentially use cousins of Newton's method to get the orbit to close. Once you've got it to close and you want to study stability, you say, okay, instead of starting at time 0, although I'll use that one, but I ask the question, if I introduce a perturbation at time 0, what happens 1 period later at time 0? Now I'm looking at a neighboring orbit, and the eigenvalues of this matrix would tell you about the linear stability properties. And if you choose an arbitrary time and go 1 period later, the periodic orbit, so you can go a period from any point in that orbit, then I can study the stability properties at any point. And the eigenstructure of this is not exactly universally repeatable, but a typical pattern is that there is one double root that's on the unit circle, and there is typically 2 other real roots. One of them is lambda, and the other one is the reciprocal of lambda, and we'll prove that to you, but it's true. And if this one is inside the unit circle, that one will be outside, or vice versa, whichever one you call lambda. So this reciprocal lambda means I have one very stable root near the origin or closer to the origin, and one very unstable root for, again, a discrete system. The unit circle is a stability boundary. And then I typically have one complex conjugate pair for the other 2 eigenvalues, and all of the lambdas have a norm except this one of 1. These 2 are these are on 1, and these have a norm of 1. So this structure is what we found in our particular study, and I hadn't beat on this globally, but I know that there are circumstances where sometimes this real pair is replaced by another complex conjugate pair, and then when you get anyway, you get near the boundary of the existence of this orbit, some funky things happen, and I haven't mapped all of those, but somebody here that has, I'll be happy to get some more tutoring. But eigenvectors that correspond to these eigenvalues, that's the key point for constructing manifolds. If you go to the most stable eigenvalue, the one that's nearest the origin, the corresponding eigenvector is a direction in a 6-dimensional state space in the general problem. And that'll be some direction. And I can tell you that if you're displaced, first of all, eigenvectors have a property. Their sign is ambiguous, because if you scale an eigenvector by a negative number, it'll be a same direction, but an opposite sense. And both sense are important. So you have a stability in either direction, but the nature of these perturbations, I'll have to let you look at them in slow time, but there is a judicious, but these things tend to spiral in tangentially. The stable ones do close to tangentially to the orbit. And the most unstable ones are the most rapid departure direction from this orbit. Well, if you think about all this a while, and it does take too long, then this is one of the L1 orbits, periodic orbits. And here, at some point, you can generate the part of the manifold that goes back toward the Earth, because the eigenvectors have 2 opposite directions. If I go in another direction, then I can asymptotically approach from manifolds that are on the opposite side of this eigenvector, the sense of this eigenvector. So there are stable orbits coming in from both sides to that manifold. And also the unstable orbits, the red ones, likewise, I can diverge toward the Earth or diverge qualitatively toward the moon in this particular figure. If you study that a while, that has implications. And so we asked the question for a typical problem, just for this idealized problem, how do we mathematically take a relatively small number of trajectories. Each one of these lines is a backward integrated in time trajectory, and I can coast forward and spiral into that orbit on if I was going to allow this, put a spacecraft on that with the correct position velocity, I would coast back into that orbit. But if I take a finite number of these, and I'm saying like order of 50, is that dense enough to interpolate all infinity of them? And the answer is yes. I'll show you that. And so order of 50 of these trajectories is enough to interpolate all the dense ones, and 50 to 60. And in fact, to interpolate them with 10 to the minus 10 accuracy, more than engineering accuracy. So these are very smooth surfaces, and they are easy to approximate if you use the right approach to do approximation. So let's talk about our good friend Chebyshev. There's a set of polynomials that are very famous. A Russian mathematician. These polynomials live on the interval from -1 to 1. So whatever your time or space variable is, you have to map it onto that interval so that the argument lies there. And I can take an arbitrary x between two limits a and b and do this linear transformation, and u will lie between mine. I can invert that for u if I wish, but anyway, this will map. This is the equation, and its inverse is the mapping that gives you the obvious way to map on linearly onto this interval. And these functions are very closely related to a finite Chebyshev series is equivalent to a finite cosine series with a change of variables, basically. So it's very closely related, and I won't prove all that. But these polynomials in the continuous domain have an associated weight function. And that is, if you integrate over take the inner product of these two functions, the ith one and the jth one, any pair of them from -1 to 1, and have a weighting function of the reciprocal of 1 minus u squared, which notice that goes to infinity as you approach the end of the interval, which seems a little strange. So you have infinite weights at the end of the interval, and you have a finite weight everywhere else. But that's the definition in the continuous world of orthogonality. And if you proceed to the discrete world, and a lot of these things you don't have to work a little bit to prove them, but I'll tell you the truth. You may or may not be able to see these dots here, but these are linearly, uniformly spaced points. These points densify at the end of the interval for the discrete case. And as a number of points go to infinity, then they become infinitely dense. And so that sort of captures the emphasis on the end of the interval like you were seeing before. But why would you do that? Well, Chebyshev and anybody that does curve fitting with uniformly sampled data, if you can, your intuition would say, if I can believe that curve fit anywhere, I should be able to believe it in the middle of the data, in the center of the data set. And if you use uniform sampling, that's exactly right. And for any fixed interval, as you approach the end of the interval, you don't have any data outside to help you approximate at the end of the interval. And so Chebyshev said, well, hey, if I'm free to measure anywhere I want to, what if I let the measurement density go toward infinity as I get close to the edges of the region of interest, and let the samples go toward infinity? Can I compensate and make the errors more uniform? And the answer is yes. And that was the intuitive motivation for the 1 over square root of 1 minus u squared, and for densifying, making the measurements more dense at the end of the interval. And so you can construct orthogonal functions, and this is a cosine distribution of the nodes. So if you just take the cosine of pi k over m, the number of measurements, that will generate this densified set of samples. And if you go through the least squares, the normal equations, this matrix, you got to invert. On the average, it doesn't invert itself. And if you go use ordinary polynomials instead of orthogonal polynomials, if you use a power series type polynomials, if you haven't done this before, you should do it as a student, because just generate data from any function and try to fit it with a power series polynomial. You'll find out that the van der Waals matrix, which is what replaces the T matrix with powers, rows will be 1 starting with 1 and T to the nth will be the rightmost number. That matrix is notoriously ill-conditioned. And if you get above about 10th order, an SVD won't help you. It's just numerically with at least with 64-bit arithmetic, you need something else to invert it. So it's not even invertible, a straight power series isn't. So basically, the consequences of that is here. I don't know what our order fit is, but you encounter something called a Runge phenomenon. Both the Chebyshev fit and the power series fit look pretty good, except near the boundary. And again, if you try to go to very high order, these arrows at the boundary called the Runge effect gets really big, but they don't with the densified data. But if you make this an orthogonal matrix by introducing the discrete version of the Chebyshev orthogonality conditions, then this becomes a diagonal matrix, and there is no matrix inverse. You just simply divide by the reciprocal of the inner product of each individual function, which squared summed over the data. And so you end up with the least square operator becomes this simple thing. The only division is by m. So the entire least square operator, which includes everything over to the W matrix, that entire C is just the Chebyshev functions evaluated at the data, and you can operate on an arbitrarily large data set with just a matrix multiplication. And if you do that, what's it worth? Well, here's a example function which I have fit. It looks like with a power series and a Chebyshev, and they all look like they lie on top of each other. But if you blow it up, or more specifically, subtract the approximation from the function, the Chebyshev sort of oscillates about 0, and the Runge phenomena is on either end. And this is for a 10th order fit. And this is about the edge of what you could do with a power series. And if you approximate with a Chebyshev function, I can go to arbitrary degree. I can do machine precision. And one characteristic of fitting with orthogonal functions is you get a beautiful behavior that on the log scale, that the error decreases linearly with the degree of the approximation. It's not exactly true for an arbitrary function, but this is characteristically the behavior is called spectral convergence, which really tells you that you're on the right track. You can take a couple of points and predict for any tolerance what degree fit you need with pretty good accuracy with using this property. And of course, you just can't do anything with a power series. So I just wanted to capture why we're doing this kind of approximation. It's not just for fun, and it applies to higher dimensions. And there's another remarkable property that if you use the same pattern and number your data judiciously, a couple of tricks are required. It turns out that here I have a cosine approximation in 2 dimensions, and you can imagine I can do it in 3 and n. Then it turns out that the higher order least square operator, and this is in 2 dimensions, is simply a product, a Kronecker product of the 2 one-dimensional least squares operators, whether you've got orthogonal functions or not, turn out to produce the least square operator for higher dimensions. And this holds for n dimensions. And so this is very powerful way to do higher dimension approximations, because the 1D Kronecker products, and there's a little there's some stories. I have to show you the details on how to justify that, but by judiciously indexing the data and naming them in the right order, you can make them so that they satisfy this Kronecker product behavior. And you can do high order least squares with just a one-dimensional operator, Kronecker multiplied. And those who haven't done Kronecker multiplications, don't be intimidated. It's nothing to it. A Kronecker product B is just every element of A multiplies the B matrix. So this is how you generate the high dimensioned Kronecker operator. And so now we look at a specific example. Here is a periodic orbit, and I've got two views of it. One is kind of a 3D view over here, and if I look down the x-axis, then I see a planar curve. And I'm introducing two non-dimensional variables. One of them is just the angular phase of the position in the orbit. And this is the epoch point, which I use the position and velocity to define the orbit. And this is some other arbitrary point. And it turns out to be the point where I study the eigenvalues to find the least stable direction. And it's kind of going tangentially back in this direction. And ultimately, you can see the visible divergence. And this is the most stable, eigenvector. And S2 is the time to go. It's the time of flight from a particular point here to get back to the point. But so we do them both. I think of it as an arc length or whatever, but it's going to be mapped onto -1 to 1 for the sake of doing these approximations. And I need about 50 or 60 of these threads, and I can interpolate that entire surface. And it's beautiful. And here's what it looks like. Here is the manifold for corresponding to an L1 family. And it's kind of hard to see which is which, but these trajectories are the ones that come in this way, kind of swing down and then come up and over. And those other lines are really hidden lines. They should be on the other side of the figure, but with no offense to my wonderful graduate student, we can do a little better on the graphics to make the hidden lines be hidden. But this surface with only a relatively small number of trajectories, this is the sum square. There are actually three curves there of X, Y, Z. And each one of those is fit with a 65th degree polynomial, but we're doing 10 to the minus 10 errors. So it's somewhere in, after you pass 50, you're in the mission caliber representation of an ephemeris. And all three of those are there, and the velocities are represented. And curiously, you can represent either position, velocity, or acceleration, because when you differentiate, when you integrate Chebyshev functions, you get back Chebyshev functions of the first kind. So integration is wonderful because it's closed. You go the other way, you generate the derivatives of Chebyshev polynomials, which are another set of polynomials. But either way works. But when you differentiate, you typically lose one order of magnitude. And if you stare at this a little bit, you can see 10 to the minus 10 up here. Position is a little bit better than velocity because we differentiated position and lost a little bit of that accuracy, but I think we can live with it. I don't know what you think, but I believe it's still pretty darn good. Velocity is almost an art form, and acceleration you can publish as an art form. But these surfaces are differentiable, and they're very nice. And now we want to say, how do we, where to from here? This is the ideal circular restricted three-body problem. Well, first of all, I can do an entire family, and let's just rotate one time or two. The red curve are the unstable, is the unstable manifold from near L1. The blue curve is the stable manifold going to a trajectory on L2. And the cutting plane is in the center of the moon. And so just by staring at this, and again, I'm sweeping energy on both sides, but look you can see, let me let this movie play one more time. If you watch right in this part, they almost lay on top of each other. And if they match position to high precision, you know they match velocity pretty close, because if you prescribe the energy is the same at that point, then the velocity has got to follow. So there's a very cheap transfer possibility to transfer from L1 to L2 by taking advantage of this intersection and just studying it. So that's pretty interesting, I think. And so, you know, the imaginary eigenvalues that we kind of ran past without saying anything about, those correspond, at least within the linear approximation, to sine cosine motions as you go around the orbit. And they generate a torus. And you can model that torus if you wish. And you might wish. I think if you're a grad student, you know, PhD, you might wish. And here, this, believe it or not, is the full high fidelity. All the gravity anomalies, the Earth Moon not in a circular relative motion, includes a perturbation of the sun. And we had to introduce a third variable, and it's the epoch time associated with the definition of the closest thing to a periodic orbit that was there exactly in the three-body problem, but it's not exactly periodic in the case of all the perturbations. And we swept the time of the epoch plus or minus 2 weeks. So this basically is a month. So you want to talk about a launch window, and we represented the entire surface, including its time variation, with just additional dimensions to the orthogonal approximation. And it works beautifully. And now, in the next 15 minutes, we're going to do some optimal control. So I'll do optimal fuel. Here we have the state space differential equations, and in the Cartesian world, the control influence matrix is an identity matrix operating on a vector u hat, which is the direction of the control, and delta is the throttle that goes from 0 to 1, and they use the standard approximation that thrust is proportional to m dot, or m dot is proportional to t over exit velocity, times the throttle, which lies in the range from 0 to 1. And so if you want to minimize the propellant consumption, you take the unsigned version of the right-hand side and you integrate over that, but T over C is constant. So the integral of the throttle turns out to be the performance index for minimum fuel. And if you look at the terminal boundary conditions for the case, we'll just do the restricted three-body problem piece of it right now, where we're only worried about, well, we'll worry about whatever's there, but the terminal manifold is actually a surface approximation, and it's a function in the case of the first example I showed you in detail of S1 and S2. So the S vector is the dimension of the approximation space, even though what we're approximating is six-dimensional. Position and velocity, so the only two-dimensional approximation space, and we are going to find the optimum S along with the optimal trajectory. So that will give us the that will tell us where we patch. So at the top we have here we augment the usual integral Lagrangian form of the Pontryagin principle. We have a Lagrange multiplier times the state differential equation written in the f of x minus x dot equal to 0 form. And we have the differential equation associated with mass flow rate and a Lagrange multiplier lambda m for that. And then over here we have the terminal constraint manifold, which again has additional variables s. So if we write the Hamiltonian with the corresponding to the integral portion of this problem, we get everything that contains delta, I pull it out by itself. And this piece over here doesn't contain delta, but I look at the throttle itself. but the Hamiltonian has to be minimized at every instant. We know the throttle is at worst 0, otherwise it's positive. So that truth allows us to stare, if you haven't done the Pontryagin logic in this setting before, allows us to stare at this thing and say, well, wait a minute, let me worry just about the direction of thrust. And you stare at this a bit and you say, well, delta is at worst positive. So the SIGN of this contribution with respect to the optimal direction of U, I'd like for you to have the direction opposite to the velocity costate vector. This is the so-called primer vector, which you may know a certain person in the audience has made a portion of his living off of a nice paper on that subject. Right? And that's a beautiful thing, by the way. So this aligning the thrust vector opposite the costate vector to make it a unit vector, we just say lambda v over the norm of the lambda v to the minus sign. And you say, okay, I'm going to go ahead and substitute that back in here. And I define all this thing as a switch function, but I evaluate it with the optimal direction of U and end up picking up another lambda up here. So I end up with a norm squared, and one of those cancels. And the S function, when you pull it out, has the norm of the velocity costate vector divided by the mass 1 minus C1 lambda m. The SIGN of this thing changes whatever is here. And it turns out that if the switch function is positive, that tells you, because it's a negative expression here, that tells you that will make this thing as negative as possible to minimize the Hamiltonian. If S is negative, it's 0. If S is 0, you call the late Hank Kelly and use the Kelly conditions to check for a singular control, which did not happen in these calculations. So we did not try to disturb him from his peaceful sleep. If you know, some people love my humor, some people don't. I'm sorry. Hank Kelly actually liked my humor. May he rest in peace. But anyway, a 2-point boundary value problem that you get here without worrying about the manifold is traditional. So this version of the 2-point boundary value problem looks pretty good. I know the initial state. I know the initial mass. I don't know the initial costate for lambda, and I don't know, and that includes both the position and velocity pieces of lambda, and I don't know the initial mass costate. And so I have here 7 unknowns and 7 initial conditions, and the terminal conditions somehow have to determine the equations that solve for the 2-point boundary value problem. However, but I have not yet considered S, and I have to do that, and that augments this 2-point boundary value problem. By the way, you didn't know you're still going to get course credit in this, did you? This is good stuff. You know, it really is. It's pretty. I just wanted to get you the feel of it, and somewhat over the fear of flying. You too can do this and have a lot of fun with it. So putting this piece into the picture, the 2-point boundary value problem it's got to be augmented in some way. But before I do that, I want to look at the fact that there's an unknown number of discontinuous switches. The first time I did this when I was a graduate student, I modified my integrator, which is, you know, some version of Runge-Kutta or her cousins. And essentially inside the integrator, if on the next tentative step, S changed signs, then I said, time out. I'm going to do, I think I did the interval halving until I essentially approach 0 from the left, because everything you do after you pass the discontinuity is wrong, because that discontinuity has to be taken into account in your Runge-Kutta integrator. So you have to approach it from the left. There are other ways to get after this. But I said, you know, really, in this program, I wanted to have a different way of handling that. And there are several other people who have worked on this problem. And Ihsan Taheri and I adopted the hyperbolic tangent as one of our favorite ways to do business. And the hyperbolic tangent sort of looks like a switch function. And it's best illustrated by replacing the sine function, 1 plus a sine function, by 1 plus a hyperbolic approximation of it, which when this parameter rho is a scalar approaches 0, the hyperbolic tangent piece approaches a SIGN term, which is the rigorous Pontryagin result. But it does so in such a way that I make my integrator automatically find those zeros to a pseudo-satisfactory degree of approximation by when I set rho to a large value, then instead of having a jump discontinuity in the throttle, it kind of acknowledges that they should be getting lower, but it's kind of smoothly. And this is just a typical switch behavior, S going through 0 twice. And as you set this parameter a bit smaller, then you see this, what should be a discontinuous coast drops down and gets more approximate. But then when I go down by an order of magnitude, now this is almost a square wave as God intended it to be. And when you go to 0.01, you can declare victory graphically, at least, even though this function is mathematically smooth in what looks like sharp corners. And what happens because it's smooth and differentiable, even though it looks totally discontinuous, you know, your integrators, if they're good, they have a Mario Andretti, if you're old enough to remember him, transmission in there that slows down when you go through the S's at Le Mans. You downshift and blow up that figure, you'll see it's a smooth function going through that, and you never have to let your integrator just worry about doing its job, and you find all of these zeros without ever having to search for them, and that's the way we solve this problem. Now let's get back to the boundary conditions with the S function. And let me just say, in the interest of time, because we're running out of that, the precious fluid of life is called time, that we end up with a condition that the velocity times the gradient of the manifold with respect to S must vanish, and that gives us the boundary condition, and it turns out to be 1 times the dimension, however many S variables we got. And if we got 2 of them, then I end up with 2 constraints that would give us what we need for the simplest case of the phase in the target orbit and the time of flight to approach that target orbit. And if I include the ephemeris time, I'd have a 3rd S. And all 3 of those were accommodated in these developments. And the 2-point boundary value problem then has the structure of, I've got a grand total of 6, 7, excuse me, I got, 6 variables here out of position and velocity. Another one for mass, I got 7, 8, 9. I got 9 unknowns, and I got 9 constraints. And therefore, I think of all of this as a root solving problem. And I don't know if you can tell it or not, but this is a 9-dimensional space. And for the fixed final time, it's the garden hose problem where I vary these variables to solve those. We have a cult you can join at my place to learn how to get started, but you have to have a way of approximating these things. And let me just say that we find a minimum time solution first, which tells me approximately how long it takes to reach the manifold under ideal circumstances. And once we find minimum time, we say, okay, let's allow another 10 hours and see what we get. And so you can map out, and ultimately you can do free final time, but you can map out various fixed final time maneuvers and find the optimal patch point. And that's how we cheated to solve this problem. But the minimum time solution is the starting fundamental solution to get an idea of what is T final. Basically, God doesn't give that to you, and we have to find it. So with that, I want to show you a particular trajectory, and this is the time of flight is 32 days, and it turns out the powered or the spiraling part of the trajectory is about half the total mission time. So the rest of this is coast. And so the powered duration was 16 days and then another 16.8 days of coasting in this case. to get to the target. We did not make the final time free in this example, but you can, but you need initial co-states, and we use the estimates, and we can get that by doing various cases en route. So we don't pretend this is just a black box. You have to have the culture of trajectory optimization to go with it, but we have come up with a method to find the patch conditions and let them float freely among all the infinity of possibilities to find the point that will coast into the target. And with that, we're just about on time, which is pretty remarkable for me. So how do we represent the manifolds? Well, I'm sure that you can represent them some other ways, but we found out that the Chebyshev polynomials just love approximating the surface, and we can do it very efficiently without any matrix inversion by integrating about 50 to 60 trajectories. And we interpolate it, and we checked it in between. We're modeling it to, for all practical purposes, close enough to machine precision to fly with. And we did that for the fully perturbed problem. The corporate, we did that. Patrick, I think you're listening on Zoom. I'm not just stealing your thunder. I respect what you've done a lot, and want to give you full credit for it. So how do we transfer onto those surfaces? Well, we can introduce it as a terminal constraint manifold once we know what it is. And relatively traditional approach can be taken, but it's got additional parameters in that manifold, and they have to satisfy the optimality conditions as well. And relatively straightforward to do that. Can we consider a high fidelity model? The answer is yes. And we can extend the parameter space and capture. Time gets everything. Time gets the fact that the Earth's orbit is slightly elliptical. Time gets the lunar ephemeris and all of its gravity anomalies, and time gets the relative position of the Earth-Moon system to the sun. If one time variable brings in all of those perturbations and one swell FOOP as God intended it to, and that's very nice. So, and how does this relate to an actual mission? Well, it doesn't take a rocket scientist, and we are rocket scientists. Once you can do a high fidelity model, and you can say, I've got a 1 month launch window for you as far as terminal states go. And if I let the initial phase go in the takeoff orbit, I've got a fourth variable, then I can tell you what the optimum time to take off is, but I can tell you any others you want to do and a set of similar calculations. And so this has utility as soon as you can start using the full fidelity model. You can use this to do missions. And I think it will happen that it's used for missions and it'll happen in your lifetime and maybe mine. So with that, I'm going to thank you. And I especially want to thank Patrick Kelly for all of his hard work to make this presentation possible. Patrick will be either the 59th or the 60th PhD. I have two guys that are, depending on who defends first, we will see who's next. And, you know, someday Patrick's going to be a professor somewhere. You know, there may even be some place in this zip code where he might fit. You guys take a good look at him. He's a horse. So with that, I'll declare victory here, and thank you all very much. I'll be happy to take any questions that you might have. Or I consume the whole hour, but at least I'm on time.
I have the microphone, but while everyone is trying to, John, great talk as always. One quick clarification I wanted was when you're doing the approximations in multivariate sense, at least
Yes.
the examples, you're more or less using the same number of data points in all
Yes.
dimensions. But is there some physical guidance as to maybe, you know, in some directions you don't need as much?
I think that we just took it uniform. We didn't have to, but it was. But in general, anytime you're doing curve fitting, the question of what degree of fit you need has to be answered in that problem. Patrick didn't show me the numerics, but I think it was more challenging, and we'd have to when we lose the ephemeris over a month, I think that was a more challenging fit. He may even use a higher degree of approximation. I don't know that for that case, but I think it was more challenging because it had a whole bunch of different physical things going into that were time varying. But in general, you use whatever dimension is appropriate. It's nice if it's close. If it's within 3 or 4 degrees, then uniform is really nice conceptual, and storage is clean and all that. But you do what's necessary and the fit. And there's a lot of there's a lot of heuristic and some theoretical way to justify that when do you truncate Chebyshev approximation. But the rule of thumb is that when the coefficients all go to 0, 4 consecutive zeros, if you go evaluate the curve at the midpoint of the widest interval, and the prediction agrees with the underlying trajectory, which I could have spit out at any frequency I want, then you can say that's a good, that's probably a good approximation. So you essentially use residuals, and the convergence has got quite a few consecutive zeros, and also we produce from one function, we produce position, velocity, acceleration, and if all 3 of those at a midpoint approximation are accurate, then you can use the fit to predict in between data points, and be certain that it's a good fit from an engineering point. Doesn't prove a theorem, but some of the most important things engineers do are not provable by theorem, but some of them are. We just don't work hard enough to go find the appropriate theorem. But I think we can do goodness of fit approximation a variety of ways, and that's a standard problem, but particularized to the Chebyshev problem.
Good.
So thanks. That was very good, insightful talk. I had a couple questions. So on the discrete mapping. So I've looked at this a couple times for different problems, the Chebyshevs versus other schemes, and at least in your case, you have at least one of the dimensions is periodic. So like
Yes.
that phase dimension.
Yeah.
And in the past, I've used Fourier series or something
Right.
in that direction, but it's
Right.
quite clever that you can stack these
Right.
in multiple dimensions.
Yeah, I think if the curve looks like a sine cosine combination, then that's probably a pretty good hint that might be fruitful to do it. However, I think there's a certain elegance to using the same, if you can get good accuracy and spitting out those data points, because you're going to have to integrate it at least that densely at time. And again, that there's no matrix to invert to get the coefficients. It's not painful, but I understand you might be able to have, from a number of terms in the approximation point of view, you may be able to take advantage of the fact that these orbits look like, when they're near circular, they look like sines and cosines, and why not just fit them that way? And you could, of course, use a Fourier series to begin with, but back to the, at least if you use the cosine distribution to do a sine cosine fit, that would not be an orthogonal fit in that setting. And just like when you take an FFT, the FFT degrades at the boundaries of the interval. And so you're back to what Chebyshev wanted to densify. So whatever method you're using to get your sine cosine fit, if it really is a sine cosine solution, then hey, you would get it. But otherwise, you'll have some issue that would have to be investigated. What is the Runge phenomena for doing a least square fit with sine cosine? Because if you use the densification of nodes, as Chebyshev does, to get the accuracy over the entire interval fairly uniform, then the sine cosines would not be orthogonal with respect to that sample location, and you'd have to invert a matrix of whatever size is appropriate. So I think that's had to be studied, but I would admit the possibility that something is better. But there's a guy named Boyd, I don't know if he's book or not, but he has a funny folk theorem in there. He says if you're doing a general curve fitting problem and you find a better set of basis functions that are better than Chebyshev, look again. But I think that's probably a little bit of hubris. I will admit that that it's not provably best for everything, but it has
Thanks.
some
So
advantages.
the other question was about just the optimal control problem in that 9D space, and when you're targeting this larger
Yeah.
surface, how do you handle the multiple solutions and arriving on that manifold surface at different
Yeah.
locations? It seems to be quite large.
Well, I haven't proven any theorems that we got that there are local extrema, but I expect there are. If it's a three-dimensional object, if there's one high, there's probably one low, and there may be others. Also the same issue is in a lot of problems I've studied where you have multiple revolutions, there are frequently a range of, so let's say 6 revolutions, 7 and 8, and there are local solutions for each of those. And so we know how to map those out, but I haven't studied the possibility that there's more than one point on the surface that satisfies the necessary conditions, but I suspect there's at least 2. But we haven't generated except the high one. I didn't look for one that was also low. But you use these problems are not theoretically resolvable. You have systematic methods that often have a lot of heuristics in them, and I know you know that. So I don't have a perfect theorem proof lemma answer for you. These are local extremal. I think there's at least one more that we didn't generate. We got another question back there.
We have an online question. They weren't sure if they missed it, but for how much integration time along the stable, unstable manifolds was the Chebyshev polynomial interpolation accurate? And is there a paper yet on the details of the Chebyshev manifold interpolation?
Paper is under consideration. It was 16 hours of real time, and it was somewhere in the neighborhood of 1/4 the Earth Moon distance, or a little bit more than that in terms of spatial length. So I would guess the order would have to go up, but at some point, anyway. But I haven't. I don't have a empirically derived answer, which would be what I'd have to do to answer it. But it would certainly not be. It wouldn't exceed 100. I'm certain. And also, you can do piecewise Chebyshevs if you don't like the high dimensionality. But anyway, I'm inclined to, just because it's modest, to take whatever the dimensionality is required. And the fact that we didn't have to increase the the curve when we put in the perturbations was a good sign. And Byron, you've been wanting to ask something. I can see it in your eyes. What you want? What do you want, young man? Sorry.
I was, John. Thank you. Very interesting presentation over here. Looking at that in an actual real world utility, how robust is this with regard to the situation, considering what the sun might influence the solutions here? Have you looked at that problem at all?
As in solar output?
Well, no, in terms of the 4-body problem, 3-body
Yeah, we
problem.
saw, we included in
perturbations of
the
yeah.
high fidelity model, we included the sun.
Ah.
So that was included. And when we did the ephemeris time, we took everything time varying in the high fidelity model, including the full lunar ephemeris, the gravity field, the Earth Moon eccentricity, Earth Moon orbit, and we included the sun over 1 month, centered on the reference orbit, but we went 2 weeks left and right, forward and back. So we did do that. And again, the restricted results would not be very good. They were just a stepping stone, because that was a nice clean problem that we could work on. And then if that didn't work out well, I wouldn't bother going to the high fidelity. But we went to the high fidelity, we included and verified it with STK that we had a good solution that had all the perturbations, including Jupiter and Sun, and the gravity anomalies of the Moon and the eccentricity of the Earth Moon orbit. So, right.
Thank you. If you have additional questions, we're having a session out in the foyer, and so please stick around and ask. You can ask further questions or have some refreshments. Let's thank Professor Junkins again for his lecture.